Thanks, David. Good afternoon, everyone. So this is sort of a bit something different, really, to what I normally talk about, and it comes about over collaborations with some marine biologists. And this is a project that's sort of taken quite a while to get to this stage, and I'll sort of allude to some of the reasons why. So, does it come? Just about. Right. So, so some of the co-workers here, you can see their affiliations down here. Most of these are marine biologists, a group led by David Sims, who's at the MBA and also at NOC as well. A former student of mine, MJOL student from Plymouth, Metcalfe, who's now in the Netherlands, postdoc, doing something completely different, and a range of other postdocs related to the marine biology project. And Andrew Reynolds, if I get on time, has done some computer modelling. So we're talking about animals, we're talking about how organisms, animals find food, which of course is a pretty much a basic function. And there are essentially, as you guys know, those of you who work on animals, essentially there are two ways to sort of live. This doesn't work, does it? You can either essentially be a couch potato sponge, as we just saw, and essentially, or a crinoid, or a brachiopod, or one of these sort of couch potato sessile organisms. You're just basically essentially sitting there waiting for the food to arrive to you. And you could, as in the case of this chap up here, be facultatively motile and just at least move and go to the door to answer the pizza delivery. Or, as we saw yesterday evening, you can be mobile and find food, and that also has some problems associated with it as well. Not least finding the food and obviously then waiting patiently to get served. The problem is that different environments and different locations, food is not distributed the same everywhere. In some areas it's homogeneous, it's predictable, it's very abundant. In other areas it's the complete reverse. It might be patchy, either geographically or temporally, spatially, or it might be a very low abundance. And so just an example of this, those of you who are interested in your food, you can use any fast food chain you like, and you'll get basically a similar map. So this is a country you might recognise, and this is the distribution of Pizza Huts in the US. And you can see that essentially if you're over in this side somewhere in an Ivy League institution, then essentially you've got so much abundant food resources around you that essentially to find it you just need a random Brownian motion. You could put a blindfold on and wander aimlessly and randomly around and you will find enough food to survive. In contrast, if you're out doing field work in the Midwest, say, or dropped in the middle of Nevada somewhere, you would need some sort of better strategy than just simple Brownian motion and random walks to find your food resources. And this is where organisms that live in these sort of environments, where food is either patchy or poorly distributed or not predictable, need some sort of search strategy in order to find their food resources. And this is a problem that has involved my colleague at the MBA, David Sims, for quite a while. And David works on sharks. And you might have seen, obviously, in the press over it was a year ago or so, where this great white Lydia was on her way to eat us, apparently, crossing the Atlantic here. She never did. And obviously, she was there looking around in the oceans for food. Well, David actually worked initially on basking sharks, not great whites, and basically, basking sharks live and feed on plankton in the oceans near surface, and that plankton is of course patchily distributed, and it's not always predictable. And in some areas you have more plankton; it's very abundant; others not. So what you find is that there are traces when you put radio tags and satellite tags on these organisms. You find that essentially they produce a trace that looks something like this. And when you analyse the step lengths, what you find is something that approximates very, very closely to a theoretically predicted optimal search strategy called a levee walk or a levee flight. And that's where you have quite a few short steps and relatively few long steps. So you sort of generally end up going in sort of one direction more or less for quite a while, looking for a nice patch of food or denser food, and you don't find it, so you take a random turn off in a direction, carry on doing that. And when you find a patch, or you're getting closer to a patch, then you start obviously moving in shorter steps around to sort of try and mine these patches. And so you get this sort of essentially a power law type distribution here, looking at move step length versus frequencies. And David and his group initially started this looking in basking sharks, where they show this relationship. They moved on to all other marine vertebrates and have shown similar relationships in all these organisms. And more recently, with some of those co-authors who were up there at the start, as part of this project, they then moved on to look at benthic invertebrates and other invertebrates. And in these patchy, low dispersed food settings, you find these levee flights everywhere in modern organisms. Interestingly, juvenile basking sharks, for instance, don't show this. So this is a pattern that is learnt by organisms through their life, by trial and error, and presumably by going hungry. And so one of the questions that David had for me was, can we look at this in the fossil record? What is the evolutionary history of these search strategies? And he asked me, probably to date, one of the weirdest questions I've ever been asked by a scientific colleague. He said, "Oh, Richard, what is the fossil record of basking shark feeding trails?" So anyway, so we moved on to then discuss fossilization, how trace fossils form, and the fact that you need obviously interaction with the sediment. So then we worked out that if we're going to do this and look at this evolutionary, we need to look at the benthos, or at least animals that are in contact with the sediment, so that we can at least preserve trace fossils of feeding. So that's exactly what we did. So this was published earlier in the summer in PNAS, but the actual project started about 6 years ago now, and that's because of a lot of issues that I'll come to in a minute. So we were looking at various trace fossils, and we sort of basically decided to look at three main groups, three main taxa. The Scalicia and all its sort of related preservational forms, formed by infaunal echinoids, Helminthoraephae and Cosmoraephae, which are these sort of traces here formed by unknown animals. But as you probably hopefully appreciate, these are all ichnotaxa that are relatively common in the rock record in some of these turbidite sequences. So we can analyse them and find these.
Just clip it.
Oh, sorry, my noise in. I've broken it. Come on, it's not going to
Forget I said it.
Okay, yeah. Right, okay. Right, where was I? Yes. So naively, I thought, okay, I can go to some of these great museums around in Europe and just basically go in, collect some of these specimens, take some photos, take some measurements. David will be able to work his magic, analysing these trails, and we'll get an answer. The problem is that the biologists are used to working on much longer trails than this, and the sort of typical trace fossils that you find, either in museum collections or in normal sort of field environments, don't have enough turns in to make his analyses statistically significant, so that we can actually distinguish between random Brownian motion or these truncated power law type distributions. He said, "Oh no, Richard, what we actually really need is something with about 50 to 100 turns in it. Ideally 200 turns would be great." And I said, "Oh, you should have told me that before I went to the museums." So we then needed, a field site, and to do this actually in terms of field work. So fantastically, this project took me, for the first time in my life, to Zumaya in northern Spain, to one of these classic trace fossil locations. These are Eocene sediments that you're looking at here. Well, Eocene basically from there, simply that line towards the back of the photo. Everything here is Paleocene. And this is the classic Zumaya section here. If anyone here teaches trace fossils to students, or any students here want to know about trace fossils, all I would say is forget about your lectures, forget about your practicals. You don't want to see trace fossils in the lab. You want to go here for a long weekend, and you will basically be able to learn everything you ever want to know about trace fossils. It's fantastic. So Zumaya is one location. We also went to the Pyrenees as well, looking at similar sort of age sediments. So these are really Eocene deep water turbidite sequences. So this is what the sort of rocks look like when you get a bit closer to them. So all these sort of sands are these turbidites coming through, and there's sort of a muddy background there. And all of these beds have trace fossils on them or in them of various types. So they're beautiful scolicia there. We get all of the preservations you might need, the ones that are on the surface of the beds, the top surface of the beds, these grooves, and then these are actually, you're looking at the underside here, one of these beds. This is a sort of Taphra helminthoxis, a bit of a washed out sort of preservation. Get some of those as well on coarser sandstone beds, and you even get the sort of rusting traces, if you like, of the actual makers themselves. You see the sandstone cast. Can I switch it off, maybe? Yeah. And I use a very high-tech system for recording these trace fossils as well. I'm going to get rid of this.
Shall we kill it?
Is that better? Yes. Phew. Can you hear me still? Great. Well, actually, can you hear me? So we have this high-tech system. I've always wanted to know find a use for former OHP acetate sheets, and there's a great use for them, and that's recording these trace fossils. So, because obviously we wanted to leave things in the field, but also couldn't actually bring these big bedding planes back. So this was the high-tech solution to it. And then we took these back to the lab, and David and the team digitized these traces. Obviously, we took photos as well to help out. And then, basically, he compared the step lengths here, distributions with the various models. And I won't go into detail of all the calculations and the stats behind it. You can read the paper yourself. But the key things are, for Helminthoraceae and Cosmoraceae, they best fit actually just composite Brownian walks. These animals that made these traces were essentially living in an environment where there was either predictable or homogeneously distributed food, and Brownian walks were good enough for them to find what they wanted. There's no levy flight needed, there's no optimal search strategy needed. One interesting side point of that is that Cosmoraceae has been interpreted by Dolph and others as actually being some sort of trap or farm structure rather than a feeding trace. And this data suggests actually it's more likely to be a feeding trace. The sea urchin traces, though, the scolicia, these informal echinoids, show these levee walks. Their distributions essentially are absolutely identical to these truncated power law distributions that you see in modern animals that are searching using this levee strategy. And this is the first time that this strategy has been found in informal echinoids. And if you remember, of course, at the present day, these are informal, but they're also informal several kilometres down in turbidite fans. To actually do this work in the modern would be pretty much impossible, financially, notwithstanding your ref results, or logistically. So we can do it here with the trace fossils. This work, and it's not often I say this, but this work has really sort of changed my view of how I now interpret a bedding plane in front of me. So here's a bedding plane, here's a single echinoid trace. This is one of the longest ones that Zumaya recorded. It's about six and a bit metres long in total. Obviously these things are informal, as I said. Clearly this animal is wandering around trying to find food. This bedding point, this place, must have had very low diversity, a low abundance of food, or patchily distributed. The animal's trying to find those patches. Other bedding surfaces are completely different. And clearly here we're looking at a patch, or we're looking at more homogeneous or abundant food. And these animals are using these short turns in this place, or one animal, we don't know. So this work is right at the start, and there are some key questions now to address, and they include: when do we find the first example of this in the rock record? How far do we actually go back? We're only in the Eocene. What other taxa, extinct or otherwise, do this? And more importantly for me, I'm really interested in okay, let's sort of look at the reverse now. So what do the trace fossils now tell us about the distribution and patchiness of food through time, through key events, or through climate transitions? And for those of you who are wandering around aimlessly thinking about a PhD, here we are. You can sort of twirl around a bit. If you go down the sort of fine, there's actually not much at the sort of usual spots. We have actually got a PhD through the Spitfire DTP on exactly this topic, and we're trying to extend this back into the Paleozoic and also through the extinction events. And if I can just have one more minute of your time. One of the key reasons that we think this is really old, this behaviour might be really, really old, is some of the computer simulation work that Andy Reynolds has been doing. And you can easily generate sort of typical sort of spiral type shapes if you just simply have a simple routine where an animal basically follows its previous trail but doesn't cross it. So you're sort of, and this has obviously been seen before in a lot of work looking at how you efficiently mine a part of the seafloor. And in the fossil record, you see a lot of these animal traces actually start with a spiral. However, the only thing you need to do to that to give you a levy-like signal is to put in random U-turns into that computer program. So just a random U-turns, and these might be obstacles in the environment, or they might be physical changes within the animal. Perhaps it gets really hungry and they decide to turn somewhere else. If you actually just put in random obstacles in there, you get a pattern, computer model pattern, very, very similar to a levee walk. So it could be that this behaviour is really ancient, and actually that's potentially really, really quite interesting. Okay, thank you very much.